Hello everyone, let's start function analysis part 2, Banach space. First of all, we have to repeat some basic definition. Metric space. What is metric space? Let we have set X. This is our set X. And D is our metric. Definition. D takes from space X X and take us positive number, positive real number. Is metric if only if satisfies these three conditions. First, dx y is always positive for all x and y. Second, and by the way, dxy is equal to 0 only in case that x is equal to y. Second, symmetric dxy is equal to dyx. And third one, triangle inequality. dxz less or equal dxy plus dyz. Let's give another definition. Ball with center and x and the radius with r is called, for all y which belongs to x is our set, distance y x is less than r, like this, inside this one. All point we take, this distance is less than r. This is ball. And third definition, what does mean convergence in metric? Xn converges to x in metric space of x with metric d. It means the distance like dxn and x converge to 0. Another definition for normed and seminorms. X is set which is vector space. We know that vector space is space that there is linearity and there is 8 axioms. Vector space plus addition and multiplication by constant from ROC. What does mean seminorm? A function row from x to positive real number that satisfies these two conditions. First, rho lambda x is equal lambda rho x. This calls homogeneity for all x and lambda from R. And second, rho x plus y is less or equal rho x plus rho y. This is for all x and y from set of x. This is called subadditivity. I give one small remark. If rho from x to R is homogeneous and subadditive, then this function is greater or equal than 0. How we prove it? Just what we have first and second condition, and we have to prove this is positive. Let's check for 0. P0 is equal to P0 times x. This is equal to 0 times px. 0 times px is 0. And px1 is equal to px1 minus x2 plus x2. Just we subtract x2 and add x2. By the second condition, this is less or equal px1 minus x2 plus px2. So what is px2? Let's take like px2 minus x1 plus x1. This is less or equal px2 minus x1 plus px1. And we can write it as equal to p absolute value of minus 1, because it's symmetric. Like we can change here x1 minus x2, px1. Okay. Now what we got px1 minus x2 from the first one is greater than equal px1 minus px2, and from the second one we got this is greater or equal px2 minus x1. Px2 minus px1. From here, what we can conclude, we can write that px1 minus px2 is from here we can write this one, px1 minus px2 is greater or equal to than minus px2 minus x1, or x1 minus x2, doesn't matter. So this is greater or equal minus px1 minus x2, this is lesser or equal px1 minus x2. So we get px1 minus px2 absolute value less or equal px1 minus x2. So what we can conclude from here, our goal was to prove that px is greater than 0 . Now we proved that this absolute value is or equal to z1, so it means px is less or equal than px greater than 0. What I did, just instead of x2 I put 0, it become p and x1 x px, because p0 is 0, less or equal px1, which is px. So we got px greater or equal absolute value px, and this is greater or equal than 0. So another definition, norm. P from x to r plus is a norm if P is a seminorm Z satisfies Px is equal to 0 only x is equal to 0. So the difference between norm and seminorm is only that in seminorm there is x, that Px can be equal to 0. So again, remark. First remark, notation, it means norm in the space of x. Second, if norm in space x is not, this is norm, then metric space in this space dxy is equal to norm of x minus y in space of x. And third thing, definition, what does mean to norm. For example, we have one norm and another norm on the same space. X are equivalent if only if exists c greater than 0 such that 1 over c x in the first norm is equal to in the second norm less or equal. It literally means that we can bound by constant these norms. So another note that if norm 1 and norm 2 are equivalent, and if xn goes to x with respect to x1 to the norm 1, then xn goes to x with respect to norm 2. This calls homomorphism, I think. With respect to norm 1. Here we can put anything. With homomorphism. Homomorphism. Okay, this was some basic knowledge that we needed for Banach space. Now we start studying Banach spaces. Banach space is a vector, normed vector space, vector space X such that is complete with respect to the norm X. What does mean space of X is complete? It means every Cauchy sequence xn converges. It means exists x in x such that xn goes to x in x. Okay, let's prove one theorem. Theorem X normed with respect to X is normed space. It's equivalent with VS means same as, like, it's equivalent first X is complete. Now if we have X normed space, so this two conditions is like equivalent. X is complete, and or if we have like absolute value of our xn from 1 to infinity converts, it's bounded. It means there exist x from x such that xn converge to x in x, space of x. So let's prove this theorem. First we have 1, we need to prove 2. What does mean complete? It means like every Cauchy sequence converges. Okay, let we say that yn is Cauchy in X. We choose subsequence ynk such that ynk plus 1 minus ynk. The subsequence is less or equal to 1 over 2k. Why we can do it? Because we know that this Cauchy means all their subsequence also converges. For all epsilon, we can find such a subsequence that this inequality is correct. So now we take xk like yn k plus 1 minus 1 nk. So the sum of nk, this is equal to the ynk plus 1 minus ynk. This is less or equal than 1 divided by 2k. This is equal to 1, I think. K equal 1 to infinity. This is less than infinity. Okay, by hypothesis that we said exists x such that this sum ynk plus 1 ynk converges to zx. So yn n plus 1 minus yn 1, it converges to x, to x small. There exists such an. So ynk converges to yn 1 plus x. So it means yn converges to yn 1 plus x. So x is complete. Oh, sorry. Here we assumed second one. From the second one, we goes to first one. So we proved complete. And now we proved proof from 1 to 2. From 1 to 2, what we have? We have complete. It means xn is less than infinity. We choose yn, the sum of xn to n, and yn minus ym is equal to xn from n plus 1 to n. So the norm of yn minus ym began. This will equal the sum n plus 1 and n. So here yn is Cauchy. So exists x such that yn goes to x. Okay, the last thing in this lecture we talk about finite dimensional spaces. X fine dimensional. Maybe what does mean semi-norm in fine dimensional? We write like this: X I and P1x is equal to norm sum of xi. P infinity of x is maximum of x1 when I is from to n. And for example, P2 to norm, it means the sum of xi square and square root. Let's prove another theorem. In Rn, every norm Px is equivalent to P2, second norm, which is absolute value x. Now we need to show that this one Px then Cx. Okay, let's prove it. Let we have a1 an is basis in x, so I can write all x like x1 a1 xn an. So px is equal px1 a1 px xn an. This is less or equal p xi, which is equal to xi, absolute value of xi, pai. We know inequality, Cauchy, for example. This is equal to xi square times this pai. This is constant, this is what we want. So this is less or equal c times x speed. So we have proved right side, now left side. Px minus py is less or equal px minus y. This is c x minus y. We had this one. Okay, we take this one. Y0, px is greater than all px. This is easy. One more thing. What does mean sphere? We have p from Rn to R continuous if px is greater than 0, which when x is not 0. And sphere is x in Rn such that absolute value of x is equal to 1. This is unit sphere. Unit sphere. So px greater than 0 for all x in this sphere. It means we take infimum px for x which is in sphere. This is equal to minimum px, which is constant greater than 0. And also S is compact. So, and also px is equal to p absolute value x times x divided by absolute value of x. This is by definition of p absolute value x. This is equal to this one. This is greater or equal absolute value x times infimum py. Y is s. This is c x. So we proved px greater or equal than cx. Okay, thank you very much. If you have any question, you can write in comment.